in the wartime. It was operational in 1942, and it was the main equipments used by the British Army, and they could defeat the very sophisticated bombers from Germany. So this is the Chemun radar, and you could see this radar is no more exist. We are working. It was working at 20 megahertz in a we call high frequency radars, and you can see this antennas are like towers and much bigger. But however, that particular time it was effective, and these are some of the sentence what I copied from or published how the World War II was being decided by one equipment that is the radar. This is the statement by Winston Churchill, who was the Prime Minister of England that time, the war time. The Germans would not have been surprised to hear our radar pulses, for they had developed a technically efficient radar systems, which was in some respect ahead of our own. What would have surprised them, however, was the extent to which we had turned our discoveries to practical effect and woven all into our general air defense systems. In this, we led the world, and it was the operational efficiency rather than novelty of the equipment that was the British achieved. So what it indicates that doesn't mean that German was ahead of the radar. They made so many radars, but they were not aware of how to use the radar to make a systems that along with the other defense systems to make it effective in the actual real war. So that British was ahead of them. That is the fate of the war. And also second sentence with the German, one of the war general, the British had from the first and external advantage never to be balanced out at any time in the whole war. Their radar and fighter control network. It was for us and our leadership to freely express surprise, and that a very bitter one, that Britain had its disposal a close mesh systems, obviously carried to be the highest level of current techniques, which supplied the British fighter command with the most complete basis for direction imaginable. We had nothing like it. So that's this. So this is the way that radar is started, and worldwide almost all the countries after war started working on radar. And this is one of the conference attended by like the Holzmeier, who invented this concept very rudimentary in 1904 in a conference. He is telling that we call there is another word there that is called Watson word, who basically invented the magnetron. So that was the one of the very truly what you call, that is a very disruptive discovery in the wartime. I showed you the Chenum radar. That was basically big radar. That is called HF radar, high frequency radars. But in the war itself, almost all the countries were trying to reduce the size of radar, and that one particular device is by Birmingham University by the Professor Watson Watt and his collaborator. They invented magnetron with the help of Naval Research Laboratory. They quickly in the wartime itself they made a very compact macro radar. Most of the radars what we are using or we are developing for armed forces are in the micro frequency rather than HF frequency. So that these two luminaries are meeting in a conference. One guy is telling, I am the father of the radar, whereas the other guy is the grandfather of the radar. So this is the way the radar history. So another thing I am trying to tell you that that time this radar was not known, and these are the called you can see the ladies, but they are not the ladies, they are the Olympics. So that was a belief. That is a belief, and it is true also in a psychological sense. This when you see the radar plot, that time the sophisticated signal processing, radar data processing, what I will discuss in my subsequent slides, it was not there. So that time they used to believe that if the women they sit in the console, continuously observe the blips in the screen, the PPI screen we call it, that plan position indicators, then they will able to tell where the aircraft is moving by manually. So these are, but they were not doing it. They are being used for the war. So they are just trying to plot where the aircraft moves. So these are the first, I can tell, the radar signal processor of the World War II. So they are using their brains to process the radar data and try to tell the command down, telling that the aircraft is coming this direction, this is the speed, this is the way it's heading. And sometimes the war happens in night. So after that, I just go to the basic things. Though radar is used for so many functions, it started with the military, but it has gone to almost every aspect of sensing and even civil applications that include the following. Used for search, that is early warning radars, and the radars are used for locating the artillery fire, the motor locating radars, air traffic control radar. All of you might have seen in every airport there is one big radar is rotating. So basically they try to aid in basically for navigation and collision evidences in the vicinity of the airport. There is navigation radars. It is used for both for aerial as well as the naval radars, and tracking. This is primarily used for military, basically to engage the missiles. Another radar is very close to camera, that is called synthetic aperture radar. It usually put on a aircraft and mostly primarily satellites, and they try to get a pictures, but in a radio frequency rather than an optical feature. Intercept, attack radars. There is a guided. Most of the sophisticated missiles are having a small radars. Mostly, we call it seekers. They try to guide the missile in the end phase to pinpointly destroy the hostile targets. Radar for identifications, and mostly the police, when you are traveling in Bangalore, you might have seen the radar. This is a continuous wave radar. From the Doppler, he can find out what the speed you are moving, and there is a other like a rendezvous. Like so, when the spacecraft or nothing try to join in the space, the millimeter wave radars are used for precise rendezvous, and the radar also used continuously for this navigation micro landings. So these are the only tip of iceberg I am showing you. But if you see the current literature, the radar has gone to almost all the fields. I am not able to cover it. However, if somebody is interested and did internet search, you can get it. So what radar does basically? The kind of information radar system produce primarily started to range, and radar is one equipment. I think any other sensing, particular sonar or any other laser cannot compete with the radar to provide the very accurate range, the velocity, azimuth, altitude, and in fact by using processing you can find the acceleration, target size, target safe, target characteristics. So the radar started with HF. I told you the Chenum in the World War it was being used to protect Britain, but it has gone almost all K band, sometimes K band, but now again we have to observe the electromagnetic energy or deflect the electromagnetic energy in some other directions, but the radar equally less. So if but that particular effect is very difficult to realize or achieved in VHF. So mostly Russian radars, and still that's why that VHF radar again coming back. Another thing is what is happening this side. I will discuss about. I have a very deliberate slide, and it may be beneficial all of you. There is a millimeter wave radar. So already I have worked in that, and I am currently working on that. And most of the cars actually, all the modern cars from Mercedes-Benz or Toyota or any big companies, particularly German companies, all are having 6 to 7, 8 radars. And these radars have become, earlier it was a little bigger, now to advance the modern chips. I'll discuss about this person. So the basic principle radar works like any other sensors. It is active sensors. So the transmitter transmits, and in a classical way we call it as a monostatic. So there is circulators. This same circulator used for transmitting signals, and the signal is coupled to the space to the antennas, and the electromagnetic goes and the echo come back, and the circulator route the received signal to the receivers, and the receivers have the sophisticated signal processors and image information extractions, and the display. And the display is basically finally used by manual observation, or sometimes this radar data is used automatically to engage a weapon, etc. So this may much more details of that what I told you. So this whatever you call transmitters is not merely transmitters. It is something like the waveform modulations. What we all of you studying in the communication and all thing. And this waveform has to be modulated. So the modulation gives the property of the waveform to not only detect the target, to classify and to improve the accuracy of the measurements. And transmitters illuminate the signal to the antenna, it goes to the target, and is comes back and collected by the receive antennas. And there is a beamformer, beam synthesizer, signal extractor, signal processor, data processor, and internal processing. And this is basically in the context of weapon system. There is a command and controls. Radar vectors are always controlled, go to a combined command and console, basically for the tactical warfare. So type of targets radar sees is land and buildings. Sometimes these are undesirables, men and vehicles, that is called surface targets. Radar can detect helicopter, UAVs, fighter aircraft, commercial aircraft, cells and rockets, missiles. The missile could be surface to air to surface, surface to surface, and radars are being utilized for the defense, space defense. Radar can try to track satellite in maybe tens of thousands of kilometers, and the satellite could be man-made or could be manual. So for any exploration, extraterrestrial exploration, radars are being used. The radar can be can be installed on a ship or vehicles. We call it a shipborne or vehicle-borne radars. The aerial radars, it could be on fighter aircrafts or big aircrafts. The spaceborne, basically satellite-based radars. So this is much more detailed. The type of target, much more details. So the type of target what radars has to detect is ship, boats, dinghies, periscopes. Periscopes basically the submarine comes up as the enemy submarine. Radar has to detect for submarine warfare. Under the surface, basically these are being known for this issues are coming due to the internal conflicts, low intensity conflict. Basically, non-state actors, terrorist and nothing, they're blowing away railway lines, and there is an accelerated problem in these things. So the radars are being used to detect these IEDs. I have one exclusive slide on this radar because we have developed these radars and it has been used by our CRPF. So that is called improvising explosive devices, unexploded ordnance, and okay. So it's okay.
Slightly.
Okay. So this is the ground is the land GMB, and the air targets are like called air breathing, like aircraft, helicopter, UAV, cruise missiles. There's the ballistic missiles, the satellite launch vehicles, civils. The radars now exclusively used. We are also working on that basically for the space debris. So when all the space full of satellites, the old satellites, and they are moving here and there, sometimes it is hazards. So radars are being used and to locate them. So these are the various applications. And not only that, I tell there are challenges. Though it's simply so easy to tell that we will detect satellites, we will detect some human beings, so you have to detect one UAV. It's not easy. So because radar signal when it goes through, it has to go through different kind of lossy mediums. The medium could be sea surface, soil and foliage. I told you ground penetrating radar. That is the air, weather, atmospheric layer, space interference. Sometimes radar will be jammed by the hostile enemies, hostile radiations, basically EW systems, and could be intentional, like some communication system can interfere radar. So the entire radar signal processing is to deal with all these interference and try to extract the radar information. So the basic function of radar, the search and detections, confirmation tracking. The tracking could be track while scan, variable data rate, high data rate. These are the advanced signal processing, classifications, high resolution imaging, target recognition, identification, threat evaluation, weapon assignment, firing, weapon guidance, skill assessment, multi-aspect observation. And I just tell you, some of you, those are on the electronic side, we talked about the modulations. So almost all the modulations being used in communication has been tried out in radar, but in different purpose. The linear FM, non-linear modulation, stepped frequency, stepped FM, stepped FMCW, biphase, polyphase, all the things. And the filtering, what we use for the signal processing, because we were working on signal systems, we were knowing all the FIR filters that we use for MTI, that basically remove clutters, that is effectively double processing, constant processing, and the ubiquitous common filter, those are used for satellite tracking or what your GPS tracking use your mobile phone. It is extensively used in radar, particularly for weapon control and fire control. And imaging, the range double processing, dependent imaging as well as independent imaging. There are various ways the radar signals are being generated basically to test the radar. There is one RF level, IF level, and these are the various ways we generate data to test the typical radar is working or not before putting the data into field. So another way of classifying the radar is in functional device, surveillance, fire control, imaging, and multifunctions. Then already these are the another way that platform wise, it could be a sea based, ground based, air based, and space already told. These are radar we built in our labs, and you can say the indigenous radars. So we have radar which range less than 10 meters, the GPR, long friendly radar. Basically, you can see mines below maybe 1 or 2 meters. And we are now working on a radar for active protection systems, basically to protect the tank. And through all imaging, their ranges are more less than that. Their ranges are 100 kilometers, basically to aircraft. We have radar 100 to 300 kilometers for surveillance for Air Force. And we have radar for 300 kilometers, 600 kilometers for long range. And there are radars, what I told you, the space debris and basically ballistic missile defense their range will go up to 600 kilometers. So the almost all the frequency what you imagine being used for radar, which is also being used for communicating other things. Radar is one of the dominant equipments which is almost all the spectrums, and they have their origin from HF, and now people are working on terahertz and some millimeter waves, and so there are various flavors of radars. When the technology of other sectors started changing, radar tried to exploit it, use it. So initially radar started with mechanical scanning, then it is shifted to electronic scanning. And electronic scanning have so many flavors. Initially it was a passive phase array. Later on, almost all the radars worldwide being shifted to like the active phase array, and they use like TR model, like transmission models having MMIC based receptors to steer the beams without any mechanical shifts. So this is the way the classical radars parabolic reflector form beams in the both sides, and that is in one dimension. And sometimes you try to beam, you distort the beam to a high coverage. These are called cosecant square beams. These are the one form that block diagram radar having classical way representations. So that is going to be a single beam. You can have a multiple horns and you can multiple beams. Initially they are doing. Now these multiple beams are being formed using a beam former. It doesn't require any mechanical way of forming the beams. Now you can directly synthesize a beam is using digital signal processing. So initially when the beam forming was not popular, most of the radar were 2D. They used to give a range and azimuth. But nowadays, due to the beam forming and multiple beams simultaneously can be formed in the elevations, so you can have a 3D radar, and this radar could be rotating or could be electronic scanning. So I don't talk about it. Basically, this is the principle how it works. So how this radar beams works. So basically, when the signal comes from a directions which is different from both sides, and then you will have a different delay in the edge elements. So the beamformer what it does, try to compensate the delays and try to form a beams coherently in the direction of the target. So this beamformer, these are the phase shifters used in a beamformer. This phase shifter corrects all these delays, relative delay among the elements, and try to focus a beam in a particular direction. Something similar to your optical beams in a lens. So this is your typical coverage of a bladed radar, where you can do simultaneously handle multiple targets. You can form a beam closely such. This we call tensors. So any missiles is coming here, we can intercept it. In addition to that, simultaneously radar can look into there could be aircraft or fighter coming some other directions. And this happens sometimes in the single radar by using the electronics schedulings and modern algorithms. So you can do all the things. So these are some of the typical hardware block diagrams for the radar or modern digital radar how it works. So each RF now possible to down convert to 8-way converters. Each 8-way data can be combined mathematically in a FPGA or signal processors, and beam can be formed and signal can be extracted. So this is a typical one radar we are having that we are using for Air Force. So you can see how the beam can play in the space. You can beam like you can put like one single transmit beam, the red one, and you can have like the 8 receive beams, and you can change quickly online. Like this is the way it will search faster, and this will search faster. This is basically for more accurate searching. So all the things can be now is done, and this type of technology is available in the country. We are doing that. So this is my introduction part. So now I'll switch over to different parts. So initially I will start to tell you an interesting thing which may excite you. This is radar being used for this ground penetration through the whole imaging. You can track a human being inside a buildings and using a radar now, using a ultra wideband signals. And these two radar we have built, and some of the results we will try to show you. So first I will talk about this. Then my top name was the modern trends. I will not talk about the classical radar. I will tell you the radar which is maybe excite you. Somebody want to research or continue his career in this radar. So this topic I will just try to give a hits of ground penetrating radar, through hole imaging radar. There is a foliage penetration synthetic aperture radar, and collision avoidance radar. There is a medical imaging radar, surveillance radar, and high resolution radar. Almost all the radar we are working. And personally I work almost maybe some 40-60% of the radar. We are running so many projects, What is the benefit of this ultra wideband radar? It is totally different. It transmits only milliwatt of the power, extremely high resolutions. It can penetrate into the ground, deep into water through the wall penetrating capability, enhanced cluster operations, counter stealth radar detection capability, terrain profiling, RF beamforming, and spectral technique for robot intercept. So what is the benefit of this digital radar? Because it is high precision, ease of signal generation, can transmit very low powers, longer battery life, spread spectrums, and high improvement redundancy, simplicity to no carrier frequency. I'll tell you what this radar how it works. Digital radar is inherently secure. But the limitation is there, they have limited range, and the range could be maximum 1 kilometers. And to generate the impulse, there are techniques are there. There's impulse, noise, and LFM. In LRD, we primarily use LFM based techniques. However, that a lot of radars are there, ground penetrating radars in noise based radar or impulse based radar. So already I discussed, I skip through these slides because always this EW radar has various benefits compared to that. So now I'll just tell you that one radar will work. So ground penetrating radar. So in this particular sites, I will tell you how we are detecting mines, and this radar now being utilized by our CRPF and border security forces. So this is a typical example of the radar you might have knowing. So this radar is used to penetrate the grounds. You can see there is antennas. So these antennas are used for horizontal scanning, and when this antenna moves by a vehicle, you push it. So you can see the grid, and here is the radar gram actually. It is not a picture by camera. The radar grams, you can see pinpointly there is a pipe. Actually, this is the pipes. So this has been detected with radar. There is a hollow, and how it works? It works based on the electromagnetic principle. When the electromagnetic wave travels through a medium, and there is a discontinuity in the mediums, suddenly there is a change in permittivity. You will get a reflection. It is similar to optical reflections, and the reflections have more intensity. If you map in a 2D spectrum, you can make out. So this is so how it works, I'll just explain you. So basically, the rule of this GPR we made, that is basically remote detection, location, identification, various buried objects, and structure through subsurface imaging, landmines. You can detect landmines, that is anti-personnel, anti-tank mines, improvised explosive devices, unexploded weapon caches, clandestine underground tunnels, buried wares, frequency-driven trade-offs, and for achieving good temporal and spatial resolutions. So how it works? It works based on the principle of directive properties of the buried object or object the boundary or parts of the electromagnetic energy to reflect it back on the target. Receiving antenna record the variation of the reflected energy. Surface of the images are related to changes in directive property. You can take typical example of the frequency versus depth of penetration of a ground penetrating radar. If you lower the frequency, the penetration is higher. Like that. Once you have the frequency, you cannot penetrate. So people are telling radars are available now. They operate at a very low frequency, maybe 50, 25 megahertz. They can penetrate up to 10 to 20 meters. And these are being used for other studies like geological explorations, finding out some sort of heritage things which is without excavation. You can do, and civil and some highway construction company are being used like that. But for us, it was more for military applications. We are trying to detect all these IEDs and all. These are typical target of the ground penetrating radars. So you can detect through electromagnetic means, and these are the fields on which radar being used to find out the explosives which buried below the thing, particularly the mines. And these are the typical war areas of Afghanistan and other places. Radar being utilized to detect the things. These are the radar grams I already told you. And the left side is a raw image using sophisticated synthetic aperture radar or range migration algorithms. You can also enhance the images. A lot of research has been done and can be done. So these are typical radar from initially we started collaboration with a Norway company to understand how it works. So this is the radar from them. This is openly available literature. So this GPR is the fastest frequency in the market. Digital frequency is used. It can generate 100 megahertz to 3 gigahertz. It uses conceptual step frequency, and it is close to FMCW, and it is very efficient. With 1 milliwatt power, you can detect up to 1 meters. The summary of this, my previous section is basically understanding of electromagnetic scattering on soil and target. We did a lot of study. Step frequency waveform to synthesize impulse. And these are the clutter removal techniques. And this omega k, Kirchhoff's and back resistance mathematical algorithms are basically synthetic aperture radar algorithm is used for this image generation algorithm. So that is one part. The not the same EW now can be used for through wall imaging. And these are basically you can see after the Taj incidents, so the project came to us. So you can see somebody is inside and is used for hostage rescue, counter-terrorism, explosive entry, search and rescue. So to detect, locate stationary moving objects, the human being through wall imaging radar is used to detect, locate through different types of walls. It can penetrate through normal wooden wall, brick walls or any concrete walls. And to run a rechargeable battery, so these are all the functionality of this radar we made to have provision for wireless videos, two different kind of whatever radars we made in Facebook levels. So these are the typical, you can see that now I'll come to the losses of the wall. With the normal signal will coming, the signals when it goes through the wall, it suffers from heavy attenuations, and that also a function of frequency. So sometimes the wall can go up to like 30 dB attenuations, and the maximum attenuation happens in the concrete walls due to the constructions of materials and other things. And then followed by normal painted wood wall, clay wall, and plywood and other things. They are almost transparent. So that is the way we can do. These are typical experiment we did. So we put the antenna outside the radar buildings, and you can see these are the two objects. Could be human beings or any furniture inside. You can see without. These are typically much more after crossing and doing some sort of processing like back projection is the image construction algorithms, followed by homomorphic filterings to clean up the signals. We get it and we can do a concept amplifying. Then after that is the final thing is used presented to the job. This is an actual radar. Radar look like we call it name is the perspective. So this capability of radar is basically you can detect human being behind the walls, and these are some of the demonstrations we did in our labs. So you can see the one person inside will get a signal like this. So these are a lot of experiments we've done. So when the person moves, you can see that these are the stationary objects, the furniture. So when the human being moves inside the wall, you can see inside the wall, you can see it. So these are called radar display. So this is like a range and bearings in a grid, like XY grid. We call it as a cross range, it's a down range. And this will give you some sort of temporal profile for the person going out, in, etc. So these radars can utilize some places like when people both GPR and TWR, when there is a lot of avalanches took place in one area in Himachal Pradesh. So they didn't have equipment, so our people went there. We helped them some places, partially to help them to dig out. There were 10 soldiers died in this particular accidents. So this radar was successful, and our team was helping them to locate any debris or some sort of Himalaya. So again, this similar to the GPR, it will also understand all the soil characteristics, the waveforms, crossings, and all the advanced algorithms. So that I told you for there is another new kind of radar, and third radar will tell you. These are the radars, and I told you active protection systems. So now you might have this time why this radar is doing what is doing in this tank. It is not doing firing anything. It is not firing missile. It is basically protecting the own tank. The tanks are vulnerable actually. All the time, you might have seen in the Russian-Ukraine war, the main target was the tank. So you might have seen the news came that so many Russian tanks have been destroyed. So basically, what happened? There is a what do you call that is a race between the weapons, basically the firing capability of the enemy tank and the protection mechanism of your own tank. So when you make a tank, but your adversary try to include the capability of the bullets and all this, what you call the kinetic energy weapons or chemical energy weapons, like the bullets capability, like the gun capability increases, then the gun can try to fire and destroy the tank. So the tank has to also do. But primarily, maybe put 10 years back, all the thing was mechanically. So tank is protected with the mechanical means. They will have a very thick boundary, so there that any bullets, nothing will pass. But now the bullets are being available, it can penetrate to that. So So these are the threats are coming to a tank. It can come through a artillery fires from enemy things, or enemy tanks or heavy tanks, or it can be come through satellites or through the drones. That is a top attack munition. They try to attack the tank from top, and there is a lot of like a rogue elements, terrorist kind of thing. They can fire a very highly explosive crude IEDs to the tank, unmanned drone vehicle. So all the threat comes. So this conventional way, the mechanical way you try to protect it, the tank became immobile, very heavy, and it became inefficient. So this is the way we know these are the threats. These are the enemy of the tank. So now radars are being used like 4 radar. Each radar try to protect particular the tank in all directions. And the radar along with there is, you can see there is one small they call countermeasures. The radar try to take the target, and this countermeasure try to fire it. So then it can destroy it. It is called hard killing. So the typical example of available on the internet, I have taken it, the radar from Israel. It is being used all this. You might have seen that there is a Palestinian-Israel conflict. This particular technique is already used because you fire so many rockets without man, the tank can be throw them out. You can protect the tank automatically by electronic means, and the electronic means is called active protection system. And the active protection, the main sensor is the radar. So the tank is protected. In the end, you can see that hard kill. In these persons, radar is useful. Radar try to intercept the target and try to destroy it. So this is one of the new kind of application of radar which was already not done. So this type of thing, what happens, like you cannot import all the things, it's not available. So we are also trying our own. This is one typical trophy. We have a net I took it. So there is a radar, and this radar is used to protect that particular tank. So this is the second type of, the third type of radar I discussed. Another radar we are working, it is very for low probability of intercept radars. You can see that though you can detect radar, you can do very sophisticated, but radar is vulnerable because always radar signal is seen by the enemy. That is called electronic warfare. Suppose when I am trying to operate my radar, my enemy can capture my signals and create a false target, try to jam you or confuse you, and sometimes they deny you all the electromagnetic spectrums by using means called jamming and deceptive jamming. So that is the reason there is always a tug of war between radar as well as electronics warfare, EW. So radar try to want to detect as long as possible the target at the farther distance, but the enemy wants the radar should not detect my aircraft. I can bomb the enemy territory and come back. So always they try to jam our radar. So, but how they will jam the radar? They should also know where the radar. So that's why entire effort goes in making a low probability intercept. So one technique is used is called spread spectrum kind of technique. So what you do, instead of sending a radar power instantaneously, you can spread over time. So we are working on this. This one radar. These are the submarine. So in this submarine, radar can be attacked. So these are typical submarine-based radars. You can see these radar antennas. These radar LPI. When the submarine comes up, everybody try to listen when the radar is on. When the radar is on, they have to try to put a anti-radiation missile, destroy the submarine. So this radar has to be like whisper. You should not radiate some kilowatt of power, 1 milliwatt. Then how to design the radar? So these are the typical some of the LPI radars we use for using ships and submarines for different companies. And these are the companies that make these type of radars. So this frequency modulated low power radar has a military and civilian need of the country. And this type of research can be continued in academics. Basically, it was a lot of academic analysis and other things to come out with the new algorithms for this LPI features radar. So now I will go to, this is I completed my ultra wideband radar, and I discussed about down penetration radar and through hole imaging radar, and I talked about the radar, how it being used to protect a tank. Why I am telling this radar? Because these are not a conventional radars, it's a very new modern trend edge radar. Then the third thing I spoke about LPI radar. Those are not a small, not a normal radar. They radiate, they whisper. They don't radiate high energy because they will be cut by the enemy EW, electron warfare systems. So I covered. Now I will go to another interesting things. No, these are the only just hints I will give you. We are working on very advanced, advanced based radars. Those are Facebook messages. So these are the techniques. So you can see the full of antennas. And these are called integrated modular mast. So one particular mast having all kind of radar and communication. That is called shared aperture concept. One single antenna can be used for communications, usually for radar. These are the very advanced techniques. Other technique is the older technique, again used with the bistatic radar. These are basically transmitter receivers we put separate, and this radar was being used for detecting stealth aircrafts. So when the radar became powerful, the enemy also tried to make the aircraft smaller and smaller electromagnetically. So the radar has to change. So one of the method I told you to go to lower frequency like VHF, HF, like Russian people do. Another method is to make a bistatic. So you transmit somewhere, put a receiver somewhere. So usually the stealth works for monostatic radars, it fails. So this is one of the project we are working, and the project already taken. This is the multistatic. So instead of putting a transmitter receiver together, you put a tagger somewhere, and you put multiple receivers, then you can have a coverage. But in this case, what will happen? There are two advantages of this type of concepts. So the enemy doesn't know that because the receiver is here, he doesn't know the receiver. So the receiver will not be jammed. Usually they try to jam the receiver, they don't know. And the transmitters, usually one single transmitter covers so much area. So very covertly you can have a coverage. So this bistatic radar serves two purposes. It basically defeat the stealth aircraft attack from the enemy, as well as it is anti-jamming. It can withstand all these EW things. Nobody can jam. So this technology has aggressively taken in our laboratory, and instrumentally I was associated with that. Now the team is working. I'm working on the project. So another project like what I told you, maybe all of you may be interested. Those are working on research. This is basically something like a camera. The radars are now being used. Gone from this HF, VHF, L band to a very compact. The radars are like a chip. Like a radar will be like some coin, you can say. So all the radars, that very transmitted receivers, I'll show you. Those are being used for various applications in automobiles and collision avoidances, used for heartbeat detections, for healthcare, and being used nowadays for what do you call that? Internet of radars, basically joint radar communication, etc. So what is the benefit of this millimeter wave? It provides high resolution and very compact because the frequency is very high. And this millimeter radar, what it gives, radar is a completely edge. Always I have shown you the radars, they are quite big. And this frequency we chose, the radar became like something like a gadget like camera. So that is the main interesting feature of this millimeter frequencies. And they are very sensitive. They can detect very, even if they can detect that gestures. Basically, I'll show you that I have one slide. The Google has produced maybe some 1 million mobile phones as a radar-based gesture sensing. So that works on Doppler actually. Earlier they were using IR sensors, but that was ineffective. So if we go through this, so this particular radar will make you. The radar also like interspace communication, collision avoidance, short-range fire control, and imaging applications. And this is now my first slide will be. I'll work on military, then I'll switch over to civil. I have some few slides on civil. I'll tell you. So this I will skip it. These are the very old technique coming back because to protect our seashore. These are very old techniques. So radar signal can go to wireless and cover it. And this OTH radar, basically what it does, where you want to see that like there is a fleet in Australia, you want to see you know how can go. Mostly it was happening in communications. But radar also use the same principle. But these are very old technique, but very low cost. You can have a surveillance inter-country. Oh, sorry, I think I am searching for something. I'll skip it. I'll go to millimeter. I'll come back from there. Sorry. Just lost my sequence. I was searching for this slide. Okay. I'll come back that one because that is not linked. I'll just focus more on the millimeter wave, millimeter radar, what we work. So what is the motivation of this millimeter frequency? So it is basically making the radar is very competitive technology. It's very equivalent to a camera. That way it's very interesting, and it has a lot of benefits compared to like the sonar or any acoustic spectrums or IR sensor or camera or laser. So already I discussed with this. So one benefit is this. You can see this. These are the frequency things. They can work on over the terahertz. Beyond 300 gigahertz per terahertz. So a lot of research is going on terahertz. how this particular thing happens. Actually, if you 10 years back, mostly these radars are being research is always funded by defense. But this radar is slightly different. So it's mostly done by the automotive company like General Motors, Toyota, Daimler-Benz, Telefunken, Siemens, Thomson CST Plus, and so they invested hugely whether this can be used and basically the automatic cruise control, blind spot detections, and making the autonomous driving, which has become a very demand in the modern society. So they invested heavily to make all the components. So whatever radar component was there, they want to miniaturize and they want to make a MMIC, micro monolithic ICs. So these are the main driving factors, and they're used for traffic management by these companies like GM, EMS. They have their already systems. The collision warning evidences, semi-automated highway control. What is the technology used for the millimeter wave? Voltage control oscillator, driver amplifier, power amplifier, mixers, all are in millimeter frequencies. And 94 gigahertz, what military being used in US. And then 77 gigahertz, mostly used for civilian in Europe, and now it is being used in all the radars, all the cars. So that is the main frequencies being allocated across the thing, and mainly that you have to develop a semiconductor devices to generate a power at the frequency of 94 gigahertz. It's not a trivial. So mostly till now also people use tubes, but if you have a very short range application, you can use a semiconductor transistor. So the antennas is quite small, and it is very increased high resolutions. And another thing is the bandwidth. Like you can get a resolution of few centimeters, local sensitivity, and it is immune to jamming. So typical Raghdan bulb calculations, you can see. Suppose I am a expand radar. I am using a 4 inches or diameter antenna. If my beamwidth is 19.2 degree, so you can see if I operate 90 to almost 1/10 I am getting. So there is a change in frequency strength. The same dimensions, I will get almost 1/10 of beamwidth. So my resolutions became like a camera. So if you go for 140, you get it. So this is a what do you call that? 70 lambda by d. So this is the calculation indicates that millimeter wave frequency has a larger potential to have a very clear imaging in the crossing dimensions. Another Doppler shift. So what this whatever I told you, the cell phone of Google, what it does, basically when you try to get a hand gestures, if you try to measure this in X band frequency, it will not be sensitive enough. You will have a maybe 1 hertz. But if you try to do the same thing in 100 gigahertz, it will create a lot of frequency changes. The frequency changes will be captured by the radar and can be used for whether you are opening your finger or closing your finger, you are moving horizontally or vertically, all the things can be captured by radar. So this sensitivity also is a function of frequency. When the frequency increases, Doppler sensitivity. Suppose your vehicle is moving 10 kmph, my Doppler frequency 1.7 kilohertz. But the same kmph, if I put 100, I will get a 17 kilohertz. So almost 10 times I will get a sensitive. I will get changes. So these can be captured and any minute motions. And I believe the radars are there, and I also believe that you can find out the wrinkles. Suppose and these are being used for heartbeat. Any other, like you are trembling, like the older men care or nothing. When you try what do you call it? Like the elderly people are falling down, radar can sense much earlier the sensors. So radar can find out the vibration inside your bodies, the Doppler frequencies. So this millimeter radar is one of the things. And one work we did, I just explained you. So these are typical radars. These radars is everything for security, range measurement of 25 kilometers. This one radar from UK we purchased, but we replaced with indigenous radar. I will just explain you. And it has a signal processing software to filter out false alarms from the non-human like movement, legion, birds, and rabbits. A new flexibility mount radar on the ground level and camera. And this millimeter radar is mainly for traffic. You can see that one car getting alert behind the car, something similar to our sonar sensor. And millimeter also not only used for radar, it can be secure communication, satellite communication, other things. So typically one example is that these radars are being used in tunnel. They take a slow moving vehicle, pedestrian, mostly night times, the light is not there, and fog things, all the camera doesn't work, but radar still try to tell you. So in the Indian scenario, we these are some sort of comparison between other sensors, computer sensor with millimeter radar. Mainly the ultrasonic, those are being used in our cars, infrared laser. But what happens, they work in a very nicely in the clear weather or this or very favorable conditions. But most of them they fail actually. Suppose the heavily rain, laser, all the things doesn't work, but radar does work. But radar is costly, always costlier than that. So that's the way. So all these autonomous moving vehicles, robots. So the major sensor is in our radar. This is millimeter wave radar. So this is a typical radar being used for UGV unmanned ground vehicles. So we objective was to design a radar in W band, the 94 gigahertz this thing. So these are the spec. We designed the radar having a field of view of 60 degrees, 5 meters to 10 meter range, and it can detect from 5 meters to 10, minimum range 5 meters. These are typical frequency modulated radar, where you have an antenna, there is a circulators, and there is a VCU, which generate that 94 gigahertz using on oscillators, mixers, and all things, and there is a signal pulse. And my work was I was working on signal pulsing, radar acquisition, signal pulse, and all that. So this is a typical radar how it works. You see, this is radar size. This is only 6 kg. The height was maybe less than 1 feet. So here how it works, you see, it's like what the light. The antenna is here. We don't rotate the antenna. Actually, we rotate a plate, and this plate works like a mirror. So this plate it rotates, and because the plate is light, so the efficiency of the motor is high. So we used to use that. So there is a motor, there is a antenna, and this is the antenna. And below this green color is the signal pulse where I was working, and there is a RF circuitry to the mixers and lock filters, etc. Right there. And there is a signal pulsing card. So this is the much more realistic view how the antenna looks like. The parameter factor, these are the signal card. An actual radar looks like this. It is around 40 centimeter height and there is 2 centimeter height. And we tried out in a real UGV. The radar is fit in there. And these are the detection. It actually tells you the obstacle. It is used for autonomous navigation. So like this millimeter radar has a various type of applications. It is being used in the older radar itself. Now it is due to the millimeter wave semiconductor devices and other technology. All the radars are being converted to very small, and I will not talk about it because these are some sort of literatures I got it from various countries. These are the things are there, and I'll give you only just what is the motivation for you. Future. The radar technology millimeter, sub-millimeter wavelength have been relatively expensive, but is now more affordable than ever. So now one radar cost maybe for 20,000 rupees. So somebody can purchase, he can do his own experiment. Even lesser than that, chips are available. Dual multi-frequency tracking classifications can be done, and this is used for identification of friend and foe, electron protection, interferometry, polarimetry, and this I told you the autonomous navigations and others used for this basically to increase the lethality of missiles by putting a sensor in the missile itself. And mainly that it is being used for whatever conventional radar is used for aircrafts, the millimeter radar is used for UAVs, all the drones. So they will have this radar will fit into that on uninhabited air vehicles, uninhabited combat air vehicles, UAVs, collision warning, sensing systems, airborne instrumental long range cruise missiles, intelligence surveillance reconnaissances, man-fight infantry portable systems, all over the surveillance, man-made targets such as personnel, low altitude, submarine perimeter systems, and detecting the war gas like sarin and bioagents. The radars are being used for all these things. So the concluding remark for this millimeter radar application is the millimeter wave 77 GHz used for civil and 94 GHz for military will enhance the capability radar. And this for military use, it will be used for RF use for missiles and missile seeker and other things like automotives, robotics, handheld devices, and main thing is the medical. So this will be one of the radar will be one of the sensors will totally eliminate this what you call the DCG and that invasive measuring things like your ultrasonics. Totally all will be replaced by this kind of radars. Indian version is not there. There is not much that is happening elsewhere in the world. So that is the conclusion, military part of this millimeter. So I have some few slides. So how much time I am having? I just know that.
One more 10 minutes. If you want, 1 more 10 minutes, 5 to 10 minutes.
So I have only one or few slides. I think I am in the right time. So that way I understand. So this is basically what I told you, that is from military side for millimeter. This will be much more interesting. Somebody wants to do PhD or something, or a student wants to make his own radar. It's better to use, listen to my slides. This one, it may excite you. So the mainly the radar technology has been in existence for several decades for military, weather, and law enforcement, and so on. In the past decades, use of radar has exponentially increased in automotive and industrial applications. The automotive application includes the front-facing radar, that is called long-range radar or medium-range radar in the context of car radar, corner reflector, and these are mainly used for adaptive cruise control, autonomous emergency braking, and corner radar, blind spot detection, lane change assistance, front view cross alert, newer application automated parking. So the 360 degree surrounding protection, body chassis and cabin application, industrial application like fluid level sensing, solid volume identification, traffic monitoring, infrastructure systems, robotics, and many more. So this radar, how it became cheaper, because these are being realized through a chips. It is using silicon germanium chips. You can entire radar can fit into a single, like maybe 2 mm by 2 mm chip. So it can generate signals from 0 to 20 gigahertz. The most popular is 1770 gigahertz because these are the chips done by Texas Instruments, Infineon, allocated on vehicular radar in many countries. And when you try to, this is really lower, and if you try to increase the bandwidth, you can use for imaging. Millimeter radar sensor can measure the radial distances, relative velocity, I told you, angle variable, and these are typical in commercial classification they made it. So what they do for long range radar means 250 meters, that bandwidth will be maybe 1 gigahertz or something. So 1 gigahertz means it will be 15 centimeter resolutions. And if you go for the short range blind spot detection, that they use 71 to 81. And for other industrial, like something what we are using, like the ISM band in 2.4 GHz, the equivalent band is coming in, but that is used for all your communications. So this is a very interesting slide. All of you look. So you may not be knowing in Bangalore itself, in all the radar may be 8 radars. So you can see that how many radar. Like one is the front and back, very narrow beam. They call long range radar. The range would be around maybe 250 meters, 10 to 250 meters. And the resolution will be 10 centimeter, and the long range radar is for automatic cruise control. So basically that it assists the driver to control speed by seeing the traffic behind and ahead simultaneously. And this medium range radar that I told you, that 79 gigahertz wala, the white color char hai, these are being used for cross traffic alerts, then blind spot detections, stop and go, etc. But still there is a gaps. Again they are using on radar, there is a short range radar being used. Their ranges is hardly 30 meters, and the minimum range is 15 centimeters, and it can provide a resolution of 2 centimeters. So this is the way, and they use around micro, they go 10 gigahertz bandwidth, etc., which is not possible in the ordinary micro frequencies. And these are the already automotive radars being used, single chip radars. There are different flavors of the chips. So there is the chips already having radar, and they have a DSP inside. You can do a FFT, etc., to make a radar and output directly comment through serial link. Another cases, like where multiple chips can be cascaded, and it can go up to 350. And these are for imaging radar, radar for parking. These are very short range. Mostly they use Doppler principles and or high resolution ranging. So I'll just show you the chips. All of you may be knowing, but so these are the chips actually. TI is made. So this is actually a 4 radar, 3 transmitter, 4 with 12 radars, you can say, in the conventional way, monostatic way. There are 12 radars built into this, and it is having serial links. I think it doesn't have that signal bounce. You can take the data, the laptop you can do signal bounce. These are the radar sensors. And here, to try to make it very compact, they put a DSP engine inside. Basically, the classical DSP processor TI C674, they have embedded that, and some memories, like a microcontrollers, there are SPI CAN buses to interface. And it can use for 100 mm cross traffic, and these are the speeds already available. It is affordable. Industry can procure this one. Radar for DSP, and this is a little bigger and used for other classes. They have like different applications. So they try to do that. And there is one interesting thing: the power supply, everything inside. It is a full radar on the chip. This is much good. 2% radar chips. So there is a 2 transmitter for receiver. And there is a power supply. You can generate inside thing, all these LDOs, like regulators, and there is a workflow generators, and these are the FFT. You can do FFT on this, and that can be transmitted data through either any flex-tray transmissible serial links or through a CAN bus, which is used in all automotives. On this example I was giving, actually I had a fortunate enough to talk to the designer. The designer itself was an Indian guy who was working in Germany. Actually, this particular project was given by Google to Siemens to try out whether this particular thing can be used in a mobile phone. So this started maybe 3, 4, 5, 6 years back. So now finally the chips is coming like this. I told you 2 mm by 2 mm chips. So initially they started a breadboard like us we do. So they started making this FMC radar. So many iteration. You can see they embedded the antenna also. There is one inductor kind of things. So slowly, these are the experiments. They finally all the thing, all the register, everything removed now. So all the radar they put in the chips only. So this can be easily fit into a mobile phone, and they have produced also. And it's very successful this one. And this radar is being used to gestures. So when you try to open your hand and without touching the screen, you can operate the mobile phone. So this is one of the classic. And these are the series of chips from Texas Instruments. So these are the imaging ke liye you can cascade for chips. So this each chips will have 12 radar. You multiply by 4, it will be 12 into 4. So it will be, I think, around 48 or 94 radars are there. You can make arrays, and you can image like this, like a camera, and like different combination can be done. And there is a long range cruise missile radar, this is the chips. And for other one, like 16, that is why I told you that blind spot detection, short range radar. And like this, these are proximity sensors. So almost all flavors are available. And these are the other additional application radar coming, car door opening, radar being used to sense, suspension control, detection. Even now that heartbeat of the children can be do, find out the vehicle occupant detection. So using the radar, you can find out the person is, the live person is there inside, without going inside. Intrusion detection, occupant classification, adult, child, fair, because that heartbeat and all things, that signature will be different from child to adult. And the driver vital monitorings, heart rates, drivers sleep state detection, passenger heal pass out, and kick to, these are all the advanced features, all are being used, radar being used with sensor for this. So one thing is coming, all of you know, maybe the 5G and 6G. So they, again the drive is coming from that side. They are using all these millimeter waves to communicate data heavily from one device to another device, short range maybe gigabits per second. So once that particular amplifier modulation technique used in communication, the radar engineer what is doing directly using here to detect a target. So the communication radar goes hand in hand. Sometimes radar goes ahead. Radar technology used for communications, particularly in World War time, it was reverse way. The radar technology was used by communications, but now ulta is reverse has happened. Now the communication engineering has gone and we are using. So the conclusion is application radar as a sensor is promising. Radar on chip has become the reality. And I told you a lot of chips are coming with joint radar communication has become the order of the day. Mostly used for sensor networks, body area networks. So you can simultaneously sense and transmit with the same chip. So one work form used for detect the target, another work form used for modulating it and sending it. And gesture detection is possible by the radar, I told you. Radars are used for home security, medical aid, Internet of Drones, Comrade and ARCOM. I think this, okay, leave it, I'll go faster. These are the same thing, ARCOM, because I don't have lack of paucity of time. These are radars like already the applicable. It's not like the theory, it's already available. The personal wearable radars, home for tracking presence, fault detection, medical respiration, heartbeat, vehicle and nothing. I just give you, I did some work. I will quickly go to that. This is already covered. These are some of the chips you can actual radar, how the radar looks like on a PCB. These are from Delphi, different company. I wish I did some work for this healthcare. This is very interesting. So they found it like all the devices. One authorizer found an estimated 70 to 90 million lives each year cardiovascular diseases. And primarily we use the sensors like non-radar based techniques as stethoscopes, the portofacilograms and electrocardiograms. But they are not effective all the applications because due to uncomfort and continuous monitoring. You don't know whenever heart particular problem occurs. So they are looking for radar, and it is a very interesting thing. Uncomfortable to monitor vital signal prolonged period. And the best choice, the question is need for superior live detection method, whether radar could be a choice? Yes. Open up possibility of measuring medical parameter of initial human aspects. Almost all kind of radar, though in a smaller dimension, CW radar, EW radar, FMCW, neutral FMCW, radar-based detection of human health is a potential method for being non-contact, non-destructive, and non-obtrusive. So he started in 70s, so people predicted radar will be used. In 90, I think they picked up, and one paper published in 90 that shows that the thing, and there's a pulse radar, only kind of range, but in case of FMCW, you can do the thing. And I already showed you the Texas chips, and this is the potential. It gives you smaller size, everything, and able to detect small movements, better penetration, see-through walls. All the benefit of the radar is used for medical treatment as well. And due to this availability of a single chip solution, including transfer, receiver, clock, ADC, or digital logic put in a single chip, so it is very much possible to make a radar for remote cardiopulmonary activities, measurement of heart rate variability, cardiac diagnosis, assessment of vessel, elasticity using pulse velocity. All the things can be measured through radar. Texas instrument, it is sensors that GI has come for medical. The strong motor performance, speed sensing, lesser ambiguity in impact allocation, error-free, calculation target range and velocity, multi-dimension sensing. The Texas system is single chip, RF CMOS chip, and innovation in sensing. The chips is a driving factor of all the thing application I told you. So that has totally created a disruption in the thinking of sensing. And this is the paper I published in a conference in last year to my experience in radar, how to apply some, because I worked on this radar earlier for other military application, but for my like some paper I was working. So it can detect this heartbeat. Through all imaging what we made, there also our radar can detect heartbeat. So I was saying that this millimeter radar, it is very much possible by radiating hardly 1 milliwatt of power, 1 milliwatt or maybe 0.1 of power, you can detect that person's remotely, very precisely, is healthy or not, his respiration rate, everything can be measured as a preliminary studies. So this finding of the paper was like this. The heartbeat of human being free space can be detected at 10 meter using a transmitter power 0.1 milliwatt and hardly using antenna size of 2 centimeters. And the often design to detect was a resolution of 3.5 centimeters. And we carried out an extensive matter simulation by using some papers. And what the conclusion, all of us, it is being reported in literature is like this. Military radar may replace these electrocardiogram devices, allowing for freedom of movement. You don't require put a what you call that electrodes to touch your thing. So the antenna itself remotely you can measure all the pulses. In future, detection, breathing, body movement, additional vital signal of human health, for further medical diagnosis, the help of millimeter radar will be tried to boost simulation experiments. So we are continuing this work because we use for military, but sometimes that literature says that people are using. So we did some work. So this is very interesting. If it is true or not, you may see this radar looks like a military radar, but this is used for detecting mosquitoes. They find out in jungle, so for 5 kilometers, how many areas, because the mosquito have a dynamic constant, so the reflection comes and they were the Doppler. So that was I saw, this is Chinese innovation. Their military radar they are using with a single pulse to find out how many mosquitoes are there. But whatever I told you, but though we try to do work here in the laboratory, but we are always less. Because since I work in defense, we work so closely, we don't know. There are so many students we work, but nobody works for defense and all. I think that is what you call a fallacy or it is some sort of irony. The irony is that we work, so many demands of the research is there, but somehow, I don't know, it doesn't happen, but it may happen, maybe it may happen. So almost all the radar I told you, by bit and pieces, we try to use the techniques. Because our military is a practical based radar. If you look at the military, we don't have much scope for research, like the lack of manpower. And even if we don't have some sort of scientists not more interested in research, more we try to make systems. When you try to make a system, you cannot innovate. So this is a contradiction. Like you try to make a hardware, you will forget. If you don't know theories, then it's not possible to make it. So it will saturate. So that is the reason only what I try to say this. All of you, some of you want to do PhD or something, or any other academic work, practical lab. The millimeter chips can be taken as sensors rather than a camera and all thing. So that gives you a lot of insights, magnetically, whatever you can do through camera, much more thing can be done through electromagnetic means. Particularly the millimeter radar is a chip, is a concept. It will be totally changed, and I believe that Bangalore almost all your car will come because the chips are hardly any cost. When these algorithms became very mature. So, and the cost will come down now. The cost will come down. Now is mostly that's available only advanced cars. When the cost became affordable, some few thousands you get a chips. Chips are 1,000, but when you develop the entire system, it is costly. Because the 8 radars are required to protect a car. 8 radars. So if you count, that money goes high. That's why the costly, that's why it is available only high-end cars. The Maruti and other things, that will come very soon. So what I try to see, almost all the technique I told you, we have tried out. Like I told you, whatever technique we are working on, these other things. But we work in a slightly different fashion. We don't work in a academic fashion. Basically, whatever already published, we try to read them, and already we are working, we will combine them. But the problem happens with the way less people actually. Hardly like you have maybe some, like radar in India, in my lab is hardly you have some 100 scientists. So 100 scientists working all the area is not possible. It is impossible. But in we saw in abroad, they work academics, industry, they work as a nation, as a whole, particularly Chinese and all, they work in a very aggressive manner. Together they try to publish papers, very new technology comes. I hope that this my lecture may create some sort of inspiration all of you. Carry forward this thing. I feel that I conveyed what we do. A lot of challenges are there. Because vast things actually. Radar is a one field what I have been working for long. So I thought that the students and since the academic audience, I thought that I'll bring out certain slides what I collected over the times will be useful for you. Some people want to do any experiments. You can have the chips because these are available in the internet. I think I finished this is my last yeah, thank you, Jai. So the future Radar is actually bright.
Okay, sir, thank you, sir.
Very wonderful, excellent talk, sir, about the radar system. And my question actually is one of the toughest areas of engineering, microwave engineering and radar. Because from my students, I mean, some people say that this is one of the toughest courses. But my question is basically, this is a solid state symposium, materials and devices. What type of materials and devices, microwave devices and materials?
That's why they put the millimeter waves.
Yeah, millimeter wave.
Yeah.
What type of materials technologies are?
Mainly the gallium, germanium, gallium arsenide, all the compounds.
Yeah.
And another research should be done on the material kind, mainly that CMOS. See, the CMOS were being used for digital. But now due to research, that's why the chips are coming. See what happened when the CMOS they make all
technology, that type of R&D, if you want to do in the country, those things.
Yeah,
Which way, how the university?
University, it will be a collaborative industry, which will be blending between like your material research, plus it will be research with this semiconductor fabs. So why this we are failing here? I found it. You might see our radars are quite big now. So if you see the material where you told, that's why I am telling. So the front end, all the materials. They are gallium arsenide, okay? That front end, it will transmit or receiver. Those are close to antenna. You cannot do that in normal CMOS. Then in between, you can use both way. Like I have MMICs are available gallium arsenide, or you can do normal silica. In the end, all are CMOS, computers, all are devices. But the question is, what we are seeing now, this whatever thing is my study says, because I am from semiconductor side, I am my AEMD from the side. So what is happening now? Due to research, innovative research. What they found that main money goes in the foundry, okay, when you are making million chips. So why that one transmitter chips is costing so 1 lakh, one computer is costing only 3,000, okay. But the computer, this digital computer is much more complexity. But that is happening because the CMOS, the customers are more in computer, digital circuit, but RF circuit very few people are taking, okay. So now the research says that the CMOS can I use for the low level amplifier? Can I use for my mixer? Can I use my oscillator? So that success you see it is happening more than 24 gigahertz onwards. So that's why you see the chips that are used by TI. It is basically they are not doing anything. They are doing the same RF. They are able to put in CMOS, complementary CMOS. So that research of the leakage current, whatever that material side properties, how to manufacture easily, that research they have done. And sometimes when they will not disclose so easily to publish it, they patent it and use it. So that is the way that cost is coming down. So the chips what I am telling the use for the TI for that this is hardly 20,000 in the net you download. But if you see that how they are possible, so they that type of material composition they never tell us. They only publish.
That is the research we need to do.
So that way the cost come down. So I told you the Indian research is not encouraging for that way. Even the amplifier, that high electron mobility, the gone oscillator, I tell you that it is a, though I was not in the material, I was part of this signal processing side, I'm from engineering side, but the project I was working, no, it is basically a material project. We started maybe 20-30 years back, because at that time the denial was there, we were trying to make a radar to put in a missile. So that time you cannot purchase component also, once they know this is a missile for our country. So we invested a lot of money. Actually, then we made all these components. That what you told you, the antenna and all, is a very precise, that mineral and all thing is a very material and that you do through electroplating and other advanced chemical process you can make. You cannot make a normal micro, just 94 gigahertz will not work. Slightly precision goes down, it doesn't work. We developed 20 years, but I'm just telling you negative side of the fallacy in Indian ecosystem how it works. 20 is your way work, since it is not a numbers, suddenly that outside the chips comes, na, they'll be cheaper than us. The entire 20 years, the effort of the professors, the student, engineers, all the laboratory, they've kept it high. So this radar, when I started, I was using indigenous thing. The radar. Slowly, when the chips came, then our laboratory itself, they abandoned our ideas. The particular team was dismantled, the particular group was closed. So again, after 20 years back, we are seeing the chips are not easily available from the country. Understood? Again, the sanction is come. We are not easy. Again, we are doing. So this is cyclic. The question is, without any indigenous research, this make in India, no, it doesn't work. It is a hypothesis. It is more like mental research has to be there. Only the patents, some papers, your own ideas you don't do. You cannot have your make in India. That is the base of everything. It is a more elusive. Without doing research, you try to make in India the concept, right? It's not true. It is a more, it doesn't work. We have seen this in the military. We have seen it. Now you will not believe that we are taking a project to make a chips.